So welcome back. Let's take the link from where I left you last time, and I used this ball for a baby in this house, and I am dropping it again under the free fall in gravity. And during if such an exercise I am doing, then what is happening, that the velocity of the ball keeps on decreasing. In your high school classes, you were told that this ball, by virtue of its position on this vertical line at a height h, has got a potential energy, which was told to you it is equal to and it has a kinetic energy which is equal to 0. The potential energy was mgh, where h is the height of the ball from the floor, and the kinetic energy right now is equal to 0, and when it drops to the floor, it achieves a final velocity, and the kinetic energy in that case is equal to half mv square. How it is, I'll come to that later on, but at the beginning I'll just give you a glimpse of calculating the force which is given in newtons like this, and the displacement which is given in meters like this, and then you are asked to calculate F dot D, which you'll see that it is equal to the work done, F the force, the magnitude of the force, the magnitude of the displacement, and of course theta. And quickly I am going through that. F dot D, I can have it like this, 1 into 2 plus 2 into minus 1 plus minus 3 into 1. I prefer to write this as 1i. It may be written I plus 2j minus 3k, and here again it can be written minus j and plus k. But I prefer to write the numbers along with these equations. If they are not given, you should substitute these values, and then I obtain 1 into 2, this into this, this into this, this into this, and I find this out to be minus 3, and the unit of F dot D, which is work done, okay, is joules. I'll explain to you joules and ergs later on in the due course of time. F is calculated as this square plus this square plus this square, which is written over here. It turns out to be minus 14, and D is 2 square plus minus 1 square plus 1 square under root, which turns out to be equal to under root 6. Because F dot D again by definition is equal to Fd into cos of theta. The cos of theta becomes equal to F dot D divided by Fd, these values, and when I substitute this, I get the value of theta is equal to cos inverse or arc cos of 3 upon under root 14 dot under root 6. So these are some very simple examples which you must be able to do in minutes time. Okay. Now, to introduce, like it is done in the high school classes, we go back to our kinematics, and in kinematics of constant acceleration, we obtain three equations: v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2s, or v square minus u square is equal to 2as. What I do is, and it is based on a previous knowledge, that if I multiply this whole equation over here by 1 by 2 into n, or m by 2, I get a relation half mv square minus half mv square is equal to ma into s, which becomes ma is the force by Newton's second law, the definition of the force, and S is the displacement. Here S has been taken displacement, so I just write it as F into S. If I write like the definition I gave for D, F dot D, so in that case, if S is equal to D, then I can write the difference of the two kinetic energies. I will tell you how it is kinetic energy and how we get this expression half mv square, etc. So half mv square minus half mv square is equal to ma dot d. Okay, this is a vector, this is also a vector. These two vectors are in the same direction, and therefore the cosine of theta, cosine of 0 is equal to this, and then we can just write this f ma as f dot d, etc., etc. Okay. So before I come back to this equation, which is the work-energy theorem, we call it theorem, I'll just tell you, give you an idea as to what is kinetic energy. In the kinetic energy, I will explain to you, this is the energy because of a body of mass m moving with a given velocity v. But here, because I am saying that this is a dynamical situation, this is a kinetic situation, so we will not talk about the velocity, but instead I will talk about the other manifest of the velocity, mass multiplied by the velocity, and I will write that mass multiplied by the velocity is equal to p. This is a vector quantity as I show here. Now we define the kinetic energy as the p dot dv. Okay, the velocity and momentum are in the same direction, and I will define the definition of the kinetic energy will be an integral of p dot dv. You will not find this kind of a explanation in most of the books. Integration of p dot dv within the limits. We start from 0 and we end up at v. I'll tell you what it looks like. So p, what is p? P is equal to mv. This is m, which is a scalar. In this case, in the situation under consideration, this is a scalar. It's not changing. So I'll write v dot dv. This is a small variation in the value of velocity, and because the velocity has to change, and then the integration sign, and again this will be a definite integral between the limits 0 to v. So what is v dot dv? V dot dv is just v dv. Okay, so I can write next this equation as integral 0 to v. M I can take out if I like, m, and now v dv. So because of the dot product over here, I get a scalar here, and from the formula that we shared before, that integral of x to the power of n dx is equal to how much? X to the power of n plus 1 divided by n plus 1, provided under a condition that n is not equal to minus 1. This is the formula. And I can write this again as, to use the formula, I'll take this m, this for the beginners. When you become fluent, you don't need this. This is equal to integral 0 to v. And of course, in this case, there is constant of integration, because this is not definite integral, but in definite integral, the constant of integration cancels out, because it is the same for both limits. So this is equal to v to the power of, I'll write 1 into dv. Now we apply the formula. This is m v raised to the power of 1 plus 1 divided by 1 plus 1, and I take my q from this relation. Okay, so this relation, and this turns out to be the beautiful relation which I have written earlier. This is half mv square. So half mv square is the kinetic energy achieved by the body if it, I'm sorry, I should have written it like this. Then I put the limits here, 0 to v, and substitute these limits. So this turns out to be equal to half mv square minus, for v, where the value 0 is put there, so this is equal to half m into 0 square, which is 0. So this turns out to be equal to half mv square. So this is my beautiful relationship for what we define as the kinetic energy, the definition of kinetic energy in kinetics, which we obtain in the kinematical relationship over here by multiplying it by the mass of the body here. The difference of the two kinetic energies is equal to the work done over there. Okay, so this is one thing. I repeat, we must repeat, because this is something which I am introducing. This is not introduced in most of the things. The kinetic energy is because of the motion of the particle, and the motion of the particle, as I told you, is in this, which I wrote for you. Okay, and I told you that there is a term in Hindi, Urdu, which I can write as joke. And this joke, for the kinetic part of the body, the mass multiplied by the velocity, and then because it is changing, so I have a dot product of this with dv, which is a small change in the value of v. Integration, I carry it out over this thing, over the limit 0 to v. I find it as, because p is defined as mv, so I write it as mv dot dv, and then I proceed like this and find out the value of kinetic energy as equal to half mv square. Okay, so I like it as I have introduced. Now, the other energy, I said, when the ball was falling and it was losing the height, I told you that the ball has a potential energy, okay, by virtue of its position. The position under the condition of constant acceleration in the downward direction, which we call the gravitational field, and we also call the acceleration due to gravity small g. So you look here, what happened in that case? In that case, okay, it's very simple. But there is something which is very, very important and which we miss. Suppose I have a ball falling released from here. Okay, the height is h, and this is the ground level where it is going to fall, and I said that this is h is equal to 0, and I can say that this is h is equal to h. Okay, the acceleration is like this, a small g towards the center of the earth. So this is in the earth's gravitational field, that this kind of a motion is taking place. So now I can say that there is a force which is acting on my ball over here or anywhere if the ball is there during its free fall. So that will be equal to, there will be a force, and that force will be equal to mg. Okay. Now, if I do the same kind of an analysis, the force being a vector, this dot dh is also, I take a vector in the downward direction. I could take it y, I could take it z or whatever you like, it doesn't matter at all. And by virtue of its losing the height or changing its height, I have again the same kind of a definition, integral 0 to h or h to 0 or whatever, this, and when I write this equation as equal to F is equal to mg, okay, dot dh, the direction of g and dh is the same, while I take, I can take, I mean, my motion could be from h is equal to 0 to h is equal to h, or it could be from here with the 0 kinetic energy, and then the kinetic energy is increasing. Anyway, in all these cases, I can say that this is from 0 to h mg, which I can write. Allow me to write this as mg integral 0 to h dh. Do you understand why? Because mg is the constant for the given mass under consideration. Okay. So we are taking the mass as constant, g is always taken as a constant close to the surface of the earth. So this turns out to be like this, and this will give, I can write mg, and how come I can write this as equal to h? 0 to h, I'll write h to the power 0 dh, h to the power 0 dh, h to the power 0 is equal to 1, because anything raised to the power of 1 is equal to 0, so I am taking advantage. It's no magic, I am just putting the value over there in order to apply this formula, which is written for not a definite integral, but here I have defined the limits, so I can write this as equal to mg. How much it will be equal to? H to the power of 0 plus 1 divided by 0 plus 1. Because 0 plus 1 is not equal to 0, therefore I can use this formula. N is equal to, is not equal. So this is, this turns out to be our beautiful relation of mgh. Okay. Now another thing which I have to discuss here is that the potential energy over here is taken as equal to 0. The potential energy over here is taken as 0. The potential energy over here is taken as 0. It may not be 0. We can take the potential energy over here to be equal to 0. In that case, the potential energy here will be negative. So, it is the relative potential energy. Like we did the relative kinetic energy. The kinetic energy at this velocity minus the kinetic energy at this velocity. So, these are the things about the kinetic energy, half mv square and mgh, which is the beautiful concept that we had potential energy, and we will see in the due course of time that there is a conservation of the mechanical energy, where during this kind of a fall that we have been talking about with the green ball, the kinetic energy plus potential energy during that fall at all points, at all instances during the fall, the sum of the two is equal to constant, is conserved. Okay, so we'll see that. So this is one kinetic energy. Kinetics has got only one attribute, and potential energy has many other attributes. Energy itself has many other attributes. So now what I take is, I take another kind of potential energy, and that is associated with the action of springs. Okay, action of the spring, I'll just tell you. Suppose I have a spring. And okay, this is a spring which is not subjected to any kind of a force. The length of the spring is something, you can call it L from here to here, and F is equal to 0. Okay. Now I attach a mass to this spring over here, and this mass, I can say that this has got a mass m, which is attached to the spring. The force over here is also equal to 0, because previously I told you that the force over here is also equal to 0. So the tension in the spring is equal to 0. There is no tension. Now, if I apply a finite force on this spring, the length of the spring, and this I'll take as massless spring, and the length increases. So this mass now connected to it is the same mass, and the force which acts on it is equal to F, some force F. If there is an equilibrium and the mass is not moving, then there has to be a force in this direction. A force has to be in this direction, opposite direction, and that has to be applied by the body to which it is attached. This force is also equal to F. You can see the magnitude is the same as the magnitude of this, but the direction is opposite. Now what happens? I can write that at this moment of time, in this situation, the length of the spring becomes L plus an extension X. Okay. So there is a force and there is an extension. The relationship that we find is that the force is proportional to X, and which I can just say that if I take X here and force over here in newtons, force is in newtons, and this is in meters, then I'll get a straight line passing through 0, and the slope here, I'll write it as K. In physics, we use the K has got a lot of meaning, because anywhere there is a proportionality, we just come out with K. This K is different, and this we say that the force F, if this is the extension which could be compression also, it can be negative also, and whatever. The force on the body of mass m under the situation of elongation, at any moment I release it, then you will see that this starts oscillating, etc. F is proportional to x and F is equal to kx. F is equal to kx, and k is the force constant. Force constant. Now, I can write the relation like this: force as a vector is equal to k, which is has got the dimensions of newtons divided by meters, k x. Okay. I can also write that if this x is very small, I can take this one, and f dot dx, f dot dx. Now this is what is going to give us a kind of an energy associated with this system, because this is newtons and this is meters. Newton to meters is joules. I'll get something like this. Okay, so this I can write as again this as m I'm sorry, this will be k x dot dx, kf dot dx, and if I have to integrate, I'll tell you how the integration takes place between the limits, again 0 to x, and the same way like I obtained before, k is a constant, this will turn out to be equal to k, and because x and dx are in the same direction, make an angle of 0, so I can write this as k integral between the limit 0 and x, this is x dx. Now this is a scalar, these two I have taken as the vectors which turn out to be equal to x dx this way, and when I work it out, and we have worked it out before, this kind of a workout, and this will finally turn out to be equal to half kx square. So this is another kind of a potential energy associated with displacement, okay, under the condition of this thing where the mass of the spring has been taken to be negligibly small, and this is how the potential energy system where we have a constant force or we have a varying force, like in the case of the spring, turns out to be this half kx square. So we have one kinetic energy, and the kinetic energy in this case also, in this case of oscillation also, that will be half mv square. The kinetic energy in potential energy of the system in the case of the free fall under gravity is equal to mgh, and it is like this. Now what I leave you at after working out these things, what I leave you with is that please try to understand when you read your books that the delta kinetic energy, delta of kinetic energy, change in the value of the kinetic energy is change in the value of the potential energy. And from here I'm just stating it just like that, the magnitude, etc. But sometimes one more thing which I have to define is that half mv square, if there is a final velocity half m vf square, and the body started with half m vi square, you may get this relation readily in your book. This is the change in the kinetic energy, and I wind up today's discussion by saying that this is equal to work done. Work done in physics. A work done which could be zero, a work done that could be positive, a work done that could be negative. For example, you have a bicycle and you are riding that bicycle. I don't know how to make it. Okay, and then this you are running on a smooth road, and suddenly you have to apply brakes. So when we apply brakes, then a work has to be done by the road on the bicycle. That will be finite. But just imagine if there is a stretch, this kind of a problem I'm going to take next, at a stretch of say 10 meters or 20 meters, the bicycle comes to a stop. Okay, there are two kinds of work which are being done. One is the work done by the road, and which we will calculate, and the other is the work done by the bicycle on the road. And if the force that the bicycle applies on the road is F, then if we do the F dot D for the work done by the bicycle on the road, then I'll get the relation of the same kind, FD cos of theta. Forget about that theta. But the thing is that when the bicycle applies the force of the same amount where the force the road is applying on the bicycle, which can be determined by Newton's third law, will be equal and opposite, equal in magnitude and opposite in direction, the work done on the road by the bicycle will be equal to 0. So, why? Because theta is not 90 degrees, okay, F is there, and if it is going to be 0, this is not 0, this is not 0, then, and this has to be equal to 0. So, the reason is that my D is equal to 0, the road does not move, and the bicycle is applying a force on the road. So this problem and many other problems I will cite, I will talk about it and do the theorem which is called the energy work theorem in the next lecture shortly. I think you must put in labor. Mentally you have to be alert, you have to apply these things, and in today's work the interesting thing is that I have defined you the potential energy of the two kinds. The potential energy by virtue of the position, in the case of a freely falling body, the potential energy associated with a spring under tension which I have removed, and the kinetic energy by virtue of its P dot dV is important, PV dot dV, the two vectors, and then integration between the limits 0 to V, which gives us in both situations, any situation, because there is only one manifest, and that it gives us the kinetic energy of a system at a velocity v as equal to half mv square. So hope you have enjoyed. Okay, meet you soon.